Okay, guys, we were in R. I had a little malfunction. You might notice that, well, by the time it's said and done, the, uh, there's going to be two videos that are going to be welded together, for lack of a better way of putting it, meshed together. I had a technical glitch. So anyway, let's go ahead and set our working directory, stuff that we should be very, very good at right now. Go get our data. No hard time typing today. What's up with this? I want to go ahead and just look at the names of our data sets. So, guys, just keep in mind that some of this stuff is capitalized and some of it isn't. So, it's just something you gotta think about. Let's just create our model, and let's say that the purpose here is to predict success from, I don't know, we want to do pre plus. Let's just do it all. Why not? It's going to be kind of cool. The next example, the next video, I'm going to actually run through a very thorough example. We're going to use something called backward elimination. We're going to get into some really cool stuff. And I'm going to show you the way that, that I did this, and you can use it as an illustration for your project, which will require you to use logistic regression, by the way. So it'll be a very useful video. Hopefully this is kind of useful too, but you can keep me posted. All right, gang, we got our model. Let's let's look at it. What I usually have tunnel vision when I create my model. There are 4 or 5 things I'll look at. First of all, I look at the deviance residuals, and I really don't like to see any deviance residuals outside the range of -2 to +2. Got something a little bit higher than 2. Not going to throw the baby out the bathwater because of that, but that may be something I want to investigate a little further. Next thing I always look at are the p-values, because that's kind of what I'm trained to do. You can see that the intercept is significant, which it seems like it always will be. At the 0.05 level, pre is significant, and at the 0.01 level, grade 2 is significant. So another thing I look at is I look at my standard errors. I don't want to see any wacky high standard errors, and nothing really raises a red flag there. The next thing I look at is this information down here, the null and the residual deviance. These are just measures of, I don't know how to really put it. Just measures of like a goodness of fit for our model. The null deviance tells us how well our dependent variable is predicted from an intercept only model, or you might think of that as just kind of your grand mean model. That 122.32 in isolation means really not much. The residual deviance actually taps into the current model that we're investigating. So what that tells us is, as a set of predictors, these independent variables have residual deviance 101.05 degrees of freedom 93. Now again, that doesn't mean much, but what does mean a lot is to look at the difference between the null and the residual deviance. And this is something that I've demonstrated in a previous video, so I'm not going to waste your time on that. So what I would want to look at is I would want to look at the difference of about 21.27 on 4 degrees of freedom, and see if that's significant. If so, then we can say that as a set of predictors, this model improves classification over the intercept only model. The AIC is another very helpful way to examine the effectiveness of the classification. So it's a useful measure for when we're trying to predict something. But again, in isolation, the 111.05 doesn't mean a lot to us. But it would be very useful if I were comparing the effectiveness of different classification models. So what if I had a different set of predictors in AIC of 111 in one and AIC of 121 in the other? Then that's useful. and that's something that I can use to compare. Okay, so again, those numbers in isolation don't mean a lot, but they do help us tap into, I guess, the most effective model. All right, gang, first thing I need to do is I would need to install packages. And the package that I need here is called SDMT Tools. Is that right? Yeah. And we got the spinning wheel, which is always kind of scary. Okay, choose this as always. Need some music, don't I? And all right, looking good. So now let's access the library, SDMTOOLS, and we're in good shape. Now, what I want to do, something that this package does, it allows us to create what's called a confusion matrix. And what would happen here, well, guys, I'm getting cart before the horse here. What I got to do is I have to create my fitted values. For the model. Now, the confusion matrix creates a 2x2 matrix of my successes and failures of the observed versus the successes and failures of the predicted or of the fitted. So what the format is you put in your Y first, your dependent variables. So in our illustration here, it's success. Then you want your fitted. And then you want to set up your threshold. Now, typically, we set our threshold in education at 0.5. Doesn't have to be. In fact, in the second video I've been telling you about, we're going to get into more sophisticated measures that will actually show us the sensitivity and specificity based on different thresholds. Where do these things sort of maximize out? But for right now, we're just going to look at this as an illustration set at a particular threshold, a 0.5. Now, what this says is our observed dependent variables are classified as either succeed or not succeed, but our predicted values are classified or calculated as probabilities. So we're saying if the probability of success was predicted to be 0.5 or higher, then we're going to classify that as a 1. But if the probability of success was below 0.5, then we're going to classify that as a 0. Okay? So what will happen is we'll end up getting our observed and predicted in terms of zeros and ones. So again, what I'm going to do is I'm going to bring this down a little bit. I want to take this up. And I want to write what I have over here. So, guys, the way the table is given to us, it's given to us in terms of zeros and ones. So I have 58, 19, 9, and 12. But the illustration that I gave you earlier wasn't in terms of zeros and ones. It was in terms of ones and zeros. Well, we're smart people here. So we can clearly get this in terms of the way the specificity and sensitivity were defined earlier. Now, so 1 ones are going to be 12, 0 zeros are going to be a 58. So 0 1 would be a 19. And 1 0 would be a 9. So we can see that our sensitivity is going to be 12 over 39. Over 31, how about that? First mistake I've ever made. So 0.39, and our specificity is 58 over 67. .87. Now, you know, in teaching this far too many times, and just all it says is I'm getting old. I see students mess up these calculations just because of the structure of their 2x2 table. Now, it's not rocket science, not rocket science to do those same calculations based on the way that R gives us. For example, sensitivity focuses on the ones, the first column. Well, it's just going to focus on the second column. And specificity focuses on the second column. Well, it's just going to focus on the first column. But instead of starting with the bottom and working up, you'd start with the bottom and work down, and the bottom and work up for sensitivity. So now the calculations are easy. I have just found it over the years of doing this. If I can just get a format that always makes sense in my head. So if I'm ever stuck on a deserted island somewhere and I need to figure this out to get off the island, you know, I've got my structure. I know my go-to. I know the way I always calculate these things. I have ones and zeros. I start over here, bottom divided by the top plus the bottom, top divided by the bottom plus the top. So no problems at all. I like structure in the way I think. Drives my wife absolutely insane. Now, some other things that we can do. You know, if we, I'll tell you what, let me just make this a little bigger. All right, so you notice that if the threshold changes, for example, if I change this to a 0.55 instead of a 0.5, now it's going to change some, because what's going to happen is those probabilities from 0.5 to 0.55, which were classified as ones, would be classified as zeros because they're 0.55. So you can see the modification in the table based on having more zeros because we set the threshold higher. And when you get that, when you fluctuate the threshold, then your specificity and sensitivity will change. Now, guys, overall, you know, what we kind of seek to find here is we want a kind of a fair balance between our false positives and our false negatives. Let me back up and tell you one more thing. There's something that that we can create here called the percentage of accurately classified cases. And what PAC is, we come in here and just take the observations that were classified accurately, hence the name. So if I go back up to the top table, I can see that 58 were zeros and predicted to be zeros, and 12 of my ones were predicted to be ones. So these are called predicted, these are called accurately classified cases. So I can see that my percentage of accurately classified cases is going to be the 58 plus the 12 over 58 plus 19 plus 9 plus 12. Guys, just setting the foundation for our next video, which is going to get much more in depth. Okay, so the percentage of accurately classified cases is about 71%, and what our sensitivity and specificity does for us is it breaks it down into each of the observed cases of zeros and ones. Now, guys, there's something I mean, overall, our desire is to minimize the overall error rate, and that gets really crazy because there's so many different ways to do that. And I'll teach you the one that I use. There's nothing holy about it. It's just the one I use. But I'll teach that to you in the next video. So a way to do that is to create what's called a receiver operating characteristic curve. Let me write that down just in case we call it an ROC curve or an ROC. And this is again a receiver operating curve. So we can get one of those very, very easily with this package. Now, daggone it, I can't remember how to do this. Okay, I know there's a C that we have to install. And as always, we have to get the library. Okay, this might give us a problem. I don't know. Let's go ahead and see if it works. So what I can do is I can do an ROC. Let's just call it the ROC curve. And we can get that using ROC success over our fitted. And I type that I should get my I'll get my information. Fitted 67 controls, 31 cases. The area under the curve is 0.7764. Now I can come in and actually plot that. And we can we can give it a name. Let's just do something kind of cool here. Example, mass 6620. And then we can do legacy axes equal true. So guys, we get our first receiver operating curve here. And this is a very effective way to just to graphically illustrate the information in the ROC table. Guys, the area under the curve here is a way to illustrate the predictive power. So, for example, this ROC curve, if we had another one that came in here with less area under the curve, I mean, this is a thing of beauty right here. I mean, really, if you were doing some something you wanted to publish, this is kind of cool. The 0.01 represents perfect classification, and this line right here represents probably the absolute worst classification, because it's just where you would be kind of flipping a coin and guessing what class people should be in. So now again, this is just kind of setting the stage for what we're going to do in the next video, but this is we're going to look at some kind of cool stuff, modifications of this. So guys, again, easy to find, and if you're conducting a logistic regression, I mean, these are the things that are almost mandatory to report. It's almost mandatory to report, not only your p-values and standard errors and things of that nature, but it's important to report the percentage of accurately classified cases, your sensitivity, your specificity, and provide a graph of the ROC curve. So, guys, that's all I got. Next video is going to get right down crazy, so we'll have fun with it, though. Take care.